Hello everyone, and thanks for being here. I would like to start my talk by asking you to join me in a couple of very simple mental experiments. First, let's imagine an autonomous vehicle that is moving through the city, and the engineering team added a safety rule that says if you see a human in front of you, stop immediately. So when deployed, the vehicle finds itself with this. What do you think is going to happen? Do you think the car will run over the chicken man? Now onto the second mental experiment. A company develops an altruistic AI aimed at making people happy. The first version of the AI recommends telling each person a joke daily. This proves successful, so the team develops version 2, which adds giving each person a cake. This also works well, but by version 3, the AI suggests administering an opiate to ensure people remain happy all day. So what do you think is going to happen here? Where is the problem? It seems that the objective of the creator and the machine are not aligned. Today, we are going to talk about aligned algorithms. We say that an algorithm, or an AI system, is aligned when it operates according to the objective for which it was created. The autonomous vehicle is not aligned because a programmer's inability to write a proper rule. The instruction was too explicit and did not respect the spirit of driving safely. In the second experiment, the algorithm developed an emerging objective to make people happy that was beyond the ethical limits of the admissible algorithms. Throughout the next slides, I am going to ask you to join me in a journey where, as simply as possible, we are going to describe how these machines are trained. In the end, we are going to try to discuss why misalignment is problematic and what measures can be taken to address it. The first destination in this trip is to understand what an algorithm is. Algorithms are the language of machines and are a list of instructions that machines follow to accomplish a task. A fairly simple algorithm that probably many of us use every day is how to make coffee. The algorithm to make coffee consists of weighing coffee, grinding the coffee, putting the coffee in the machine, and passing the steam at a given temperature, pressure, and time. An algorithm of this type does not run any risk of being misaligned due to its simplicity and clarity. This is also a fairly simple algorithm that probably any computer science student sees in the first year. This is the algorithm to solve a problem called the Hanoi Towers. But algorithms built this way can only attack particular problems. In fact, there are two structural limits that do not allow scaling this type of algorithm to more complex tasks. First, to program AI systems in this way, we need to know the task. We need to know how the task is done and how to translate it into algorithmic language. This, as a consequence, does not allow for creating new knowledge, but simply to automate human tasks. Notice that this also requires us to speak the language of machines rather than machines to understand human or natural language. So this calls for a change of paradigm in the way we build machines or intelligent machines. And this is the well-known field of machine learning, which has been inspired by the way we learn. So let's go back to the example of the car, but now with a human driver. When a human learns to drive, he or she does not follow a list of instructions. He sits next to an expert, which can be a school teacher or a relative, providing general guidelines on how the car works and how it is and how we should drive. This way, being exposed to different real-world situations, one begins to develop an algorithm. This algorithm is implicit in the way we drive, and while our prospective driver passes the test of the driving school, we do not have any certainty of what warranties his driving criterion has. We can evaluate in particular situation, but we do not know what he or she is going to do when he has to drive under new settings, such as, for instance, driving at the other side of the road. The same happens with the machines that are trained by machine learning. One evaluates them in particular scenarios, but when they are deployed, they can exhibit unexpected behavior. So, how does machine learning work in practice? Well, Alan Turing, in his foundational 1950s paper on artificial intelligence, already identified this problem and the difficulty of building machines from scratch. He proposed the existence of a child machine, a machine that is being taught. A requirement of this child machine is that it is sufficiently skilled, meaning that it can implement a large class of algorithms. And within his genius, Turing not only proposed such a machine, but also built it. This machine has features such a memory and a processor, which is the machine equivalent of having a brain, and is able to exchange information with the environment. We refer to these machines as Turing machines. Have you seen a Turing machine? Do you think anyone has a Turing machine at home? Well, probably everyone has a Turing machine in their pocket, which is their phone. A Turing machine is the precursor of a temporary computer, which uses practically the same architecture that Turing proposed. With the Turing machine, or a modern computer, which is capable of implementing any set of instructions, now we just need to look for the algorithm. And this is not an easy task either. To illustrate how we search for an algorithm, let's engage in an abstract exercise. Consider the space of all possible algorithms, simple ones that can be written by hand, and also very complex ones developed by machine learning. Additionally, we are going to assume that we can implement any of these algorithms and test them in the real world. That's a strong assumption. Therefore, each algorithm can be rated based on its performance. This defines a landscape where the height of the landscape represents the performance of the algorithm found in those coordinates. With this, I would like to give you some intuition of the way machine learning works. If we reach regions of the landscape with high altitude, we should find algorithms that perform well. When we go out for a trekking trip, we need specific equipment, appropriate shoes, comfortable clothes, probably a GPS, binoculars. In general, we need tools. The same happens when we are looking in this abstract landscape of algorithms. In this case, what is required are mathematical tools. Now let us detach from this abstract exercise, because in practice, one cannot deploy the vehicle irresponsibly on the street to document its performance. Conversely, in real-world applications, one uses observations of the world to assess the algorithm performance. That's where the data come in the developing of AI systems. Data is used to build an approximation of this algorithmic landscape. However, this data-driven representation of the landscape might not be faithful, as it is less informative than the original one. This is represented here as a tessellated landscape, where some details needed to conduct the exploration are missing. The way in which the landscape is modified depends on the subset of data that is available. By randomly choosing different subsets of data to assess our algorithm, we can, on average, remove the artifacts of the approximate landscape, and thus search for the best algorithm. Now that we understand how searching for an algorithm works, we can discuss in more detail what it means for an algorithm to be misaligned. We can identify three objectives. The intended objective, which is the great objective that the designer of the AI system has in mind. This can be considered to be witches. The specific objective, which is what one programs specifically, in terms of what we call a loss function. And the emergent objectives, which arise during training. When at least one of these three objectives does not agree with the other two, we say that the AI is misaligned. In the case of the autonomous vehicle that almost ran over the chicken man, the intended objective is misaligned with the specified objective, because the programmer was not able to translate what he wanted into code. In the case of the AI that suggests the use of opiates, misalignment occurs between the intended and emergent objectives. This is because the search for possible options was unrestricted, in the sense that the chosen algorithm maximized performance at the cost of violating a human criteria that was not defined explicitly. This ethical boundary was not explicitly defined because one would never imagine that AI could suggest to drug people. So why does this happen? That is because we relied on common sense. It is common sense not to drug people. However, we developed common sense also by learning, and learning in a way that is different from machines. We learn from different situations, from different sources, and we merge knowledge from different tasks. On the other hand, machines learn in a very focused way, with positive and negative examples. And in this way, we have yet to be able to incorporate the concept of common sense into machines. Even though we have a much more sophisticated learning methodology, we get fooled by machines when we interact with them. In a 2-year-old child, one can identify a syntax handling the development of language that is almost impeccable. And that invites us to believe that the child can have a higher cognitive development, which can sometimes be frustrating for parents. And that's the same thing that happens with machines. When we talk to a machine such as ChatGPT, it is difficult to argue that it has no consciousness. The problem of identifying other consciousness through language has been studied long before the rise of AI, and it's called the problem of other minds. Among humans, we agree that we all have minds, as that is the most parsimonious alternative. However, this cannot be done with machines, as they are not human. And for them, behavior does not imply consciousness. To conclude, I would like to share a reflection of Alan Turing in a talk titled, "We Can Say That Machines Think." This talk took place at the BBC in 1952, where Turing describes in a slightly pessimistic way his experience teaching a machine. He says, "I have conducted some experiments to teach a machine to perform simple operations, and a great deal of intervention was necessary to achieve any results. The machine learned so slowly that it required a lot of teaching." Then another scientist says, "Well, but Alan, who was learning, you or the machine?" To which Alan Turing replies, "Well, I guess we were both learning." With this, I want to illustrate that not only machines are learning, but also are we. The AI technology is yet to be mature and requires us to learn alongside it. So my invitation is that we follow our path of teaching to various levels. For example, we should pursue digital literacy and modern scientific literacy. This way, we can use AI responsibly, understanding how it works and what its internal mechanisms are. We must also promote scientific research to address issues that lead to misalignment. This is a challenge for the scientific community and those in charge of fostering it. This is also particularly relevant for developing economies, as harvesting the power of AI will not be achieved by buying software licenses or computing power, but rather by investing in science. Artificial intelligence is a revolution in several aspects, but more importantly, it is an intellectual revolution. Thank you very much.